Hello students, welcome to EPG Pathshala. I am Dr. Vidya-mitra from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Magnetic Properties 5 from paper Electronic, Magnetic and Optical Properties of Materials. From this module, students may get to know about the magnetostriction, dependence of magnetostriction on magnetic field, magnetostriction of single crystal, magnetostriction as a function of field and crystal direction. From this module, students may get to know about when its substance is exposed to a magnetic field, its dimensions change. This effect is called magnetostriction. It was discovered as long as ago as 1842 by Joule, who showed that an iron rod increased in length when it was magnetized lengthwise by a weak field. The fractional change in length delta L by L is simply a strain, and to distinguish it from the strain epsilon caused by an applied stress, we give the magnetically induced strain a special symbol lambda, which is equal to delta L by L. The value of lambda measured at magnetic saturation is called the saturation magnetostriction lambda S, and when the word magnetostriction is used without qualification, lambda S is usually meant. The longitudinal, sometimes called the Joule magnetostriction just described, is not the only magnetostrictive effect. Others include the magnetically induced torsion or bending of a rod. Magnetostriction occurs in all pure substances. However, even in strongly magnetic substances, the effect is usually small. Lambda S is typically of the order of 10 to the power minus 5. The small magnitude of this strain may perhaps be better appreciated if it is translated in terms of stress. If Young's modulus is 30 into 10 to the power 6 lp per inch square, the normal value for iron and steel, a strain of 10 to the power minus 5 would be produced by an applied stress of only 10 to the power minus 5, that is 300 pound per inch square or 0.2 kg per millimeter square or 2 megapascal. Alternatively, the magnetostrictive strain can be compared to thermal expansion. Metals and alloys typically have thermal expansion coefficients near 20 into 10 to the power minus 6 per K. So, a strain of 10 to the power minus 5 results from a temperature change of just 0.5 Kelvin. In weakly magnetic substances, the effect is even smaller, by about 2 orders of magnitude, and can be observed only in very strong fields.
Although the direct magnetostrictive effect is small and not usually important in itself, there exists an inverse effect which causes such properties as permeability and the size and shape of the hysteresis loop to be strongly dependent on stress in many materials. Magnetostriction, therefore, has many practical consequences, and a great deal of research has accordingly been devoted to it. The value of the saturation longitudinal magnetostriction lambda S can be positive, negative, or in some alloys at some temperature it is 0. The value of lambda depends on the extent of magnetization and hence on the applied field, and figure 1 shows how it typically varies with H for a substance with positive magnetostriction. As mentioned in the preceding chapter, the process of magnetization occurs by two mechanisms, domain wall motion and domain rotation. Most of the magnetostrictive change in length usually occurs during domain rotation. Between the demagnetized state and saturation, the volume of a specimen remains very nearly constant. This means that there will be a transverse magnetostriction. It very nearly equals to 1/2 the longitudinal magnetostriction and opposite in sign, or lambda t is equal to minus half lambda. It causes an equal expansion or contraction in all directions. Forced magnetostriction is a very small effect and has no bearing on the behavior of practical magnetic materials in ordinary fields. The measurement of longitudinal magnetostriction is straightforward but not trivial, especially over a range of temperatures. While early investigators used mechanical and optical levers to magnify the magnetostrictive strain to an observable magnitude, today this measurement on bulk samples is commonly made with an electrical resistance strain gauge cemented to the specimen. The gauge is made from an alloy of wire or foil grit embedded in a thin paper or polymer sheet, which is cemented to the sample. When the sample changes shape, so does the grid, and the change in shape causes a change in the electrical resistance of the gauge. With ordinary gauges, the fractional change in resistance is about twice the elastic strain. It causes an equal expansion or contraction in all directions. Forced magnetostriction is a very small effect and has no bearing on the behavior of practical magnetic materials in ordinary fields. The measurement of longitudinal magnetostriction is straightforward but not trivial, especially over a range of temperatures. While early investigators used mechanical and optical levers to magnify the magnetostrictive strain to an observable magnitude, today this measurement on bulk samples is commonly made with an electrical resistance strain gauge cemented to the specimen. The gauge is made from an alloy of wire or foil grit embedded in a thin paper or polymer sheet, which is cemented to the sample. When the sample changes shape, so does the grid, and the change in shape causes a change in the electrical resistance of the gauge. With ordinary gauges, the fractional change in resistance is about twice the elastic strain. This is typically a small resistance change, but one fairly easily measured with a bridge circuit, either AC or DC. Capacitance or inductance or optical measuring systems of various designs may also be used. These have the advantage that nothing has to be cemented to the specimen, and by appropriate design they can be used over a wide temperature range. Careful control of the sample temperature is always necessary, since, as noted above, a 1 degree temperature change can easily produce a strain larger than the magnetostrictive strain to be measured. Thin film samples present special challenges in the measurement of magnetostriction. Since the films are almost always bonded to a non-magnetic substrate, if the substrate is thin enough, a change in dimension of the film may produce a measurable curvature in the substrate, from which the magnetostrictive strain can be deduced. Another approach is to apply a known stress to the sample and measure the resulting change in magnetic anisotropy. This method makes use of the concept of the stress anisotropy, as described later in this chapter.
Magnetostriction of single crystals. When an iron single crystal is magnetized to saturation in a 100 direction, the length of the crystal in the 100 direction is found to increase. From this, we infer that the unit cell of ferromantic iron is not exactly cubic but slightly tetragonal. A tetragonal cell has 3 axes at right angles, 2 are equal to each other and the third is longer and shorter than the other 2. This conclusion follows from what we already know about the changes occurring in an iron crystal during magnetization in a 100 direction. If the saturated crystal is longer in the direction of its magnetization than the demagnetized crystal, and this single domain which comprises the saturated crystal must be made up of unit cells which are slightly elongated in the direction of the magnetization vector, must be made up of unit cells which are slightly elongated in the direction of the magnetization vector.
The same is true of each separate domain in the demagnetized state. Figure 2a depicts this state in terms of 4 sets of domains 1 0 0, 1 bar 0 0, 0 1 0 and 0 1 bar 0. Unit cells are shown by dashed lines. Their tetragonality is enormously exaggerated and so is their size relative to the domain size. But the main point to notice is that these cells are all longer in the direction of the local ms vector than they are in directions at right angles to this vector. Thus, when a region originally occupied by say a 0 1 bar 0 domain is replaced by a 1 0 0 domain by the mechanism of wall motion, that region must expand in the 1 0 0 direction and contract in directions at right angles. The length of the whole crystal therefore changes from L to L plus delta L, where delta L by L is equal to lambda S, the saturation magnetostriction in the 1 0 0 direction. The unit cell of iron is exactly cubic only when the iron is above the Curie temperature, that is, only when it is paramagnetic and subject to no applied field. As soon as it cools below Tc, spontaneous magnetization occurs and each domain becomes spontaneously strained, so that it is then made up of unit cells which are slightly tetragonal. The degree of tetragonality in iron and most other materials less than can be detected by X-ray diffraction, so iron is regarded as cubic in the crystallographic literature.
There are therefore two basic kinds of magnetostriction: spontaneous magnetostriction, which occurs in each domain when a specimen is cooled below the Curie point, and forced magnetostriction, which occurs when a saturated specimen is exposed to fields large enough to increase the magnetization of the domain above its spontaneous value. Both kinds are due to an increase in the degree of spin order. The spontaneous magnetostriction is difficult to observe directly, but it is evidenced by a local maximum at Tc in the variation of the thermal expansion coefficient with temperature. This is the reason why Invar, an iron nickel alloy containing 36% of nickel, has such a low expansion coefficient near room temperature. Its Curie point is near room temperature and its spontaneous magnetostriction varies with temperature in such a way that it almost compensates the thermal expansion. The ordinary field-induced magnetostriction, which concerns us and in which lambda changes from 0 to lambda s, that is shown in figure 1, is caused by the conversion of a demagnetized specimen made up of domains spontaneously strained in various directions into a saturated single domain specimen spontaneously strained in one direction. Figure 2 shows one special case of such a conversion in which the only mechanism of magnetization change is domain wall motion. Domain walls are described by the angle between the ms vectors in the two domains on either side of the wall. Two types exist: 180-degree walls and non-180-degree walls. The iron crystal of figure 2a has only 90-degree walls. Nickel, which has 111 easy directions, can have 180-degree, 110-degree or 71-degree walls. Non-180-degree walls are often called 90-degree walls for brevity, whether the actual angle is 90-degree, 110-degree or 71-degree. The domain structure of real single crystal is normally such that both 180-degree and non-180-degree walls exist. The magnetostrictive effect of the motion of the two kinds of walls is quite different, because the spontaneous strain is independent of the sense of the magnetization. The dimensions of a domain do not change when the direction of its spontaneous magnetization is reversed. Since passage of an 180-degree wall through a certain region reverses the magnetization of that region, we conclude that 180-degree wall motion does not produce any magnetostrictive change in dimensions. Magnetization of the iron crystals of figure 2 is accomplished by 90-degree wall motion and a change in the length of the crystal does occur. Rotation of the MS vector of a domain always produces a dimensional change because the spontaneous magnetostriction depends on the direction of the MS vector relative to the crystal axis. Thus, in the general case of a crystal being magnetized in a non-edge direction, the magnetization process will involve 180° and 90° wall motion and domain rotation. The last two of these three processes will be accompanied by magnetostriction.
Cubic crystals. The saturation magnetostriction lambda S undergone by a cubic crystal in a direction defined by the direction cosines beta 1, beta 2 and beta 3 relative to the crystal axis when it changes from the demagnetized state to saturation in a direction defined by the direction cosines alpha 1, alpha 2 and alpha 3 is given by lambda S is equal to 3 by 2 lambda 100 into alpha 1 square beta 1 square plus alpha 2 square beta 2 square plus alpha 3 square beta 3 square minus 1 by 3 plus 3 lambda 111 into alpha 1 alpha 2 beta 1 beta 2 plus alpha 2 alpha 3 beta 2 beta 3 plus alpha 3 alpha 1 beta 3 beta 1, where lambda 100 and lambda 111 are the saturation magnetostrictions when the crystal is magnetized and the strain is measured in the directions 100 and 111 respectively. This equation is valid for crystals having either 100 or 111 as easy directions. Most commonly, we want to know the strain in the same direction as the magnetization. Then beta 1, beta 2 and beta 3, and equation 3 becomes lambda st or lambda s is equal to 3 by 2 lambda 100 into alpha 1 to the power 4, alpha 2 to the power 4, alpha 3 to the power 4 minus 1 by 3 plus 3 into lambda 111 into alpha 1 square alpha 2 square plus alpha 2 square alpha 3 square plus alpha 3 square alpha 1 square. This can be further reduced by means of the relation alpha 1 square plus alpha 2 square plus alpha 3 square whole of square is equal to alpha 1 to the power 4 plus alpha to the power 4 plus alpha 3 to the power 4 plus 2 into alpha 1 square alpha 2 square plus alpha 2 square alpha 3 square plus alpha 3 square alpha 1 square, which is equal to 1, to the expression lambda st is equal to lambda 100 plus 3 into lambda 111 minus lambda 100 into alpha 1 square into alpha 2 square plus alpha 2 square into alpha 3 square plus alpha 3 square into alpha 1 square. Equation 3 is called the two constant equation for magnetostriction. Like the rather similar equation for crystal anisotropic energy, it can be expanded to higher powers of the direction cosines. The next approximation involves 5 constants. Its use is rarely justified by the accuracy of available magnetostriction data. Equation 3 and others derived from it require a word of caution. They give the field-induced strain when the crystal is brought from the demagnetized to the saturated state. The saturated state is, by definition, one in which the whole specimen consists of a single domain with its MS vector parallel to the applied field. The demagnetized state, on the other hand, is not well defined.
All that is required is that all the domain magnetizations, each properly weighted by its volume, add vectorially to 0. The difficulty is that there are an infinite number of domain arrangements and relative volumes that can result in 0 net magnetization of the whole specimen. Equation 3 is based on a particular definition of the demagnetized state, namely one in which all possible types of domains have equal volumes. For example, in a cubic crystal like iron with 100 EG directions, this state is one in which the total volume of the crystal is divided equally among 6 kinds of domains: 100, 1 bar 00, 010, 01 bar 0, 001 and 001 bar. If this ideal demagnetized state is not achieved, equation 3 is invalid and the measured magnetostriction will be larger or smaller than the calculated value. Differences in the magnetostriction values observed by different investigators for the same material are usually due to differences in the demagnetized states of their specimens.
Lambda st is equal to 3 by 2 lambda 100 into cos square delta minus 1 by 3. This is the strain along 001 which occurs when an ideally demagnetized crystal is saturated in the direction delta. When delta is equal to 0, this expression reduces to lambda st, where lambda is equal to 0 is equal to lambda 100 as it should. If we take the state of saturation along 001 as the initial state, then the strain along 001 in a single domain when ms rotates by an angle delta away from 001 is delta L by L is equal to lambda st, delta is equal to delta minus lambda s2 delta is equal to 0, which is equal to 3 by 2 lambda 100 into cos square delta minus 1 by 3 minus lambda 100 which is equal to minus 3 by 2 lambda 100 sin square delta. In iron, lambda 100 is positive and 100 is an easy direction. Therefore, when ms rotates through an angle of 90 degree out of an easy direction, the domain contracts fractionally in that direction by an amount 3 by 2 lambda 100. The ms vector may rotate away from 001 in any plane, not only 010, and equation 6 will still apply because a change in the plane of rotation changes only alpha 1 and alpha 2. In as much as these appear only in terms involving beta 1 or beta 2, both 0, they do not affect the final result. These several changes in the length of the crystal along 001 are illustrated in figure 3b. If the demagnetized state is non-ideal, the zero of strain in this diagram will be shifted up or down and the lambda st values shown will become lambda s values. However, the strain delta L by L resulting from a change from one saturated state to another will remain the same.
These results show that magnetostriction constants can be determined without any uncertainty regarding the demagnetized states by making strain measurements as the ms vector rotates from one orientation to another in a saturated crystal. For example, lambda 100 can be determined by cutting a disk from a crystal parallel to the plane 010. A strain gauge is cemented to the disk with its axis parallel to the chosen direction of measurement, namely 001 as shown in figure 4. The disk is then placed in the strong field of an electromagnet. When this is done, the disk magnetostrictively strains, of course, but this strain is ignored. With the disk in the position shown, the strain gauge reading is noted. The disk is then rotated by 90 degree in its own plane to make 100 parallel to ms, which is parallel to the applied field, and the gauge reading is again noted. The difference between these two readings multiplied by minus 2 by 3 gives lambda 100 according to equation 6. Actually, it is better to cut the disk parallel to 110 because this plane contains both 100 and 111 directions. Then lambda 100 and lambda 111 can both be determined from measurements on a single specimen. By this technique, without any reference to or knowledge of the demagnetized state, we can determine the value of lambda 100. For example, even though lambda 100 is defined as the strain in 100 occurring in a crystal when it passes from the ideal demagnetized state to saturation in 100. A nickel crystal contracts in all three principal directions when magnetized, as shown in figure 6. From the observed contraction in 111 direction and the fact that the easy direction in nickel are 111, it follows that the unit cell of ferromantic nickel is slightly distorted from cubic to rhombohedral, with one cell diagonal, the one parallel to the local direction of magnetization, slightly shorter than the other three. So when the ms vector in a domain is rotated away from a 1, 1, 1 EG axis, that axis becomes longer. One can then understand by arguments similar to those given above for iron, while lambda 100 and lambda 111 are both negative in nickel.
Note that in figure 5, magnetostriction is plotted against magnetization, while in figure 6, magnetostriction is plotted against magnetic field H. These qualitative descriptions of the variation of lambda with H or M below saturation can be made quantitative without much difficulty, although certain rather arbitrary assumptions have to be made about the sequence of 180° and 90° wall motion. If the magnetostriction of a particular material is isotropic, we can put lambda 100 is equal to lambda 111 is equal to lambda st. Then equation 3 becomes, with the introduction of a new symbol, lambda theta is equal to 3 by 2 lambda st into alpha 1 square into beta 1 square plus alpha 2 square into beta 2 square plus alpha 3 square into beta 3 square minus 1 by 3 plus 2 into alpha 1 alpha 2 beta 2 plus alpha 2 alpha 3 beta 3 plus alpha 3 alpha 1 beta 1, or lambda theta is equal to 3 by 2 lambda st into alpha 1 beta 1 plus alpha 2 beta 2 plus alpha 3 beta 3 whole square minus 1 by 3, which is equal to 3 by 2 lambda st cos square theta minus 1 by 3, where lambda theta is the saturation magnetostriction at an angle theta to the direction of magnetization, measured from the ideal demagnetized state. If theta is the angle between the two directions defined by cosines alpha 1, alpha 2, alpha 3 and beta 1, beta 2, beta 3, then cos theta is equal to alpha 1 beta 1 plus alpha 2 beta 2 plus alpha 3 beta 3. Because of isotropy, no reference to the crystal axis appears in equation 7, and the magnetostrictive effect can be illustrated quite simply by figure 7, which shows a demagnetized sphere distorted into an ellipsoid of revolution when saturated, for a positive value of lambda st. Figure 6 shows that the magnetostrictive behavior of nickel is approximately isotropic, and equation 7 is often applied to nickel.
So students, let us summarize what we have learned in this module. We learned about the brief description of the magnetostrictions was given, dependence of magnetostrictions on magnetic field and magnetostriction of single crystal you learned, and the magnetostriction as a function of the field and crystal direction was also discussed.